Okay, so in this video, we're going to take a look at optimizing kernels and specifically concepts like spatial and temporal locality, and also techniques like tiling and tile matrix multiplication. So the premise or the key idea here is this fundamental constraint that modern CPUs do arithmetic operations far faster than they can fetch data from memory. So one memory trip costs on the order of hundreds of multiply adds. So that is essentially the scale of the problem that we're taking a look at. And this is a significant problem because a lot of the operations and computations that we do actually involve fetching data from memory. And hence, if memory access is slow, then that indeed is a significant bottleneck. So what is the defense against this problem? So the CPU has basically a hierarchy of smaller, faster memories in defense of this problem. So of course you have DRAM, which is the main memory, and then you have a series of caches, and then of course you have the registers that are extremely fast. And in this video, we're specifically going to take a look at the caches. So essentially the cache is a bet by the CPU. And this bet is essentially the fact that it keeps recently touched data close to itself or close to the CPU, wagering that you'll want it again soon. So that is the bet that is central to the idea of a cache. Now, there are essentially two approaches to exploit the cache bet. The first is spatial locality, and the second is temporal locality. And both of these techniques manipulate different axes or levers, and that's what we're going to be diving deeper into. Spatial locality manipulates the where axis. So the central idea here is that memory doesn't move in single numbers, but it moves in fixed chunks or cache lines. If you access a value in a memory address, its neighboring values are also fetched by default by the CPU for free. And because of this, it makes sense to process the neighboring elements along with the actual value that you fetch from memory. The TLDR over here is that the memory addresses close to each other should be processed together. Now, temporal locality manipulates the when axis. And the main idea here is that if you process a value from memory, process it again soon while it is still resident in the cache. And the reason for this is that memory accesses from main memory are slower. And hence, when we do fetch a value from memory and it is still resident in the cache, it makes sense to process it again soon if indeed there is a necessity to process it at a later point, instead of just refetching it again from main memory. So now the key insight when it comes to spatial and temporal locality is this concept of access patterns, or the way in which we access the data that we are processing. Now, optimizing a kernel is largely just about rearranging the same operations so that the cache's bet pays off and we fetch fewer times from main memory, which is extremely costly. Now, in any kernel, there's essentially two main components. One is the central core math to the kernel, which determines how much work you do. And that's largely fixed. Now, access patterns is something that we can manipulate as programmers. And access patterns is essentially an art or a skill where we realign or rearrange the same mathematical operations to just make it much more convenient from a memory perspective. And this actually determines how much we need to wait or fetch from memory. Okay, so now let's take a look at spatial locality with the concrete example of the matrix multiplication kernel. So in matrix multiplication, we take in two input matrices A and B, and we produce an output matrix C. And each element of C is essentially a dot product of a row of A and a column of B. So when we take a look at the matrix multiplication algorithm, we are iterating over each row in A, and then we iterate over each column in B. And then the innermost loop is essentially computing the dot product of that row of A and that column of B that we picked. And this algorithm is encapsulated in the form of this code, which essentially just does the same thing. And I think this is fairly standard to understand. So now, in this naive implementation of matrix multiplication, we can actually take a look at the access patterns of matrices A and B. Okay, so one important thing to keep in mind is that matrices are stored in row major order, which means that elements in the same row are stored contiguously in memory. So with this in mind, let's take a look at the access patterns of A and B. So for A, we are iterating through each row in A. And then for each row in A, we are essentially walking down the elements in that row. So the access pattern for A looks pretty good because we are processing when we load an element from A, we are also processing its neighbors, which are elements in that same row. Okay, so now let's take a look at the access patterns for matrix B. So in the matrix multiplication algorithm, we iterate through each column of B. And then for each column of B, we essentially walk down the elements in that column. Now, for fairly large matrices, these elements that are placed down the same column might be located really far apart in memory. And this means that whenever we load an element of B, we are not processing its neighbors in memory, which violates the fundamental rule of spatial locality, which states that whenever we load any data from memory, we should try and process its neighbors in memory, because the way that we load data from memory is in the form of cache lines. So this is problematic. The access patterns for B are not optimal when it comes to spatial locality. So let's try and find a solution to this. So the key here is to fix the suboptimal access patterns for matrix B. And the fix is clever, yet remarkably straightforward. So we just reorder the loops of the matrix multiplication so that we iterate both A and B in row major order. So in this snippet of code, our outermost loop remains the same. We iterate through each row in A. And then our second loop, we iterate through the common axis of A and B, which is K. And then we fix a particular value of A. And then in our innermost loop, we iterate through B through a particular row in B in row major order. So if you take a look at the access patterns for both A and B, we are accessing consecutive elements in row major order. And by fixing the access patterns of matrix B, we have ensured that the matrix multiplication kernel now is optimal with regards to spatial locality, which means that whenever we fetch data from memory, we process the neighboring elements of that data in a consecutive fashion. And for the curious audience, this simple 3-line fix improved the performance of the matrix multiplication code in my machine to approximately 50x better. Okay, so now that we have optimized the matrix multiplication kernel from a spatial locality perspective, let's examine how this code holds up to the temporal locality lens. And just to recap what temporal locality is, let's just go to the definition again. So the main idea here is that if you process a value from memory, process it again soon if it needs to be processed later, and process it while it is still resident in the cache instead of refetching it for a later use. So here is the currently most optimal code, which has been optimized for spatial locality. So, and also let's just assume that A, B, and C are n by n matrices just for simplicity. So here, let's take a look at the access patterns for matrix A. So the access patterns for matrix A are already quite effective and optimal with regards to temporal locality. And the reason for that is that in the loops, we essentially fix a value of A and then reuse it across the innermost loop. So each element of A, once fetched, is fully exploited before we release or evict it from the cache. And A's access patterns are thus optimal, and we perform roughly of n squared reads of A from memory. And now let's take a look at the access patterns of B from a temporal locality lens. And this is where things get really interesting. So here, for each iteration of I, we basically iterate k times j times. And kj is basically the size of the matrix B. And thus, for each iteration of the outer loop, we are basically streaming or loading all of B repeatedly. And this can get very problematic when matrix sizes grow really large. And we can see from this access pattern where we are loading all of the elements of B across the outer loop, it roughly comes to cubic reads of B in the worst case from memory. So for B, for each iteration of the outermost loop, we fetch all of B's elements, and this is clearly not optimal from a temporal locality lens, which says that we ideally need to reuse whenever we fetch from memory. And as I mentioned, there's n cubed reads from B from main memory across this matrix multiplication kernel. And now finally, we can just take a look at the access patterns for matrix C. So for matrix C, we perform writes only, and the writes to C are performed in the innermost loop. And although this looks a little bit inefficient because the writes happen for a particular combination of I comma j across this middle k loop, the important thing to keep in mind is that the writes actually happen in row major order, which means that across the k loop, this particular row of C is resident in cache. And thus, we don't need to go to main memory for performing the fetches of C of I comma j. And thus, for a particular row C of I, for the matrix C, this row is written repeatedly, once per k, but it's just one row which stays resident in the cache across the whole k loop. And thus, in this code, we perform roughly of n square trips to memory for C, and this is done across the matrix multiplication kernel. And thus, we come to the conclusion that A and C are efficient with regards to temporal locality, but B is not. And the reason for that is quadratic or O of n squared trips to memory for A and C, but O of n cubed trips to memory for B. And this is clearly an example of lopsided reuse, which we will find a solution to now. Now, the fix for this lopsided reuse is a single key insight. And that insight is that currently we are buying reuse only in a one dimensional way. But matrix multiplication is actually a 2D problem. So, the reason why that happens is that in the outermost loop of the matrix multiplication, we are essentially holding a row of A and then doing reusable work across that one row of A. So basically, this is a 1D hold, and it buys reuse in one direction only. But the downside for this is that we need to sweep through the entire 2D extent of B every time in order for this single single dimension reuse of A. Now, the TLDR version of the fix is basically, instead of doing a 1D hold, is to hold a small 2D square tile of both matrices A and B and finish all of the work of those two tiles before evicting them from the cache. And this fundamental concept is called tiling. Okay, so now let's take a look at why this tiling approach works in the first place. So, what do two smaller tiles cost us? So, we have one A tile, which is B by B, and we have a B tile that is B by B. So, that's roughly two B squared numbers sitting in the cache. But how much work do these two tiles support? So, every element of the A tile gets to multiply against B different elements of the B tile. So, that's roughly B cubed multiply adds just from 2B squared loaded numbers. And we can take a look at that more concretely by assuming a tile size of 64. So for this case, we load about 8,000 numbers, and we extract over 250,000 multiply adds before touching main memory again. So loads grow as B squared and work grows as B cubed. And that gap, that is the reuse. So every number we fetch now pays for itself multiple times over, and crucially, this applies to both matrices at once, not just one or the other. So we don't have any more of the lopsided reuse. And the total effect of this is that B's reads collapse from n cubed to n cubed over B. So that's roughly B times less traffic. So actually implementing the tile matrix multiplication is a whole video on its own. But the point of this video is actually just to understand the why. Because there was a long time where I never really understood why tile matrix multiplication works. And we introduced two central ideas today, which is spatial locality and temporal locality. And tiling just falls out of that. And these two techniques allow us to take a look at kernels and to think about how we can optimize them. And that's essentially what kernel optimization is. It's basically just rearranging the operations or the math in a way that is friendlier for the cache. So yeah, I hope this video was useful, and thanks for sticking by.